Every game is made out of a few basic building blocks. Once you understand these techniques, you can get creative, combine these elements in different ways, and create many unique games easily. In this class, we will cover many of them, from keyboard and mouse controls to performance-friendly sprite animation tips and tricks, and the main focus this time is object pool design pattern. We will use it for enemies and for player projectiles, because reusing our objects rather than creating and discarding them over and over can be a massive performance benefit. Today, we are building an animated 2D game completely from scratch, with no frameworks and no libraries, using just plain vanilla JavaScript and HTML5 canvas.
Analysis successful. Enemy contact confirmed. It seems that our lasers are triggering a cellular mitosis in this species. How peculiar.
What does that mean?
If we shoot them, they divide into multiple smaller critters.
Ah, so we first have to split them and then we target the clones?
Yes, that seems to be the most potent strategy. Let's divide and conquer.
The entire game revolves around the planet. Literally, we control a spaceship and we need to defend the planet from asteroids and all different kinds of aliens and space bugs. This project is completely standalone and independent, but I designed the art assets to be compatible with Space Invaders game we built before, and at the end I will show you how to take sprite sheets from that game and implement them in this project with just a few lines of extra code. This class is for creative coders who want to learn about the fundamentals of 2D game development, as well as for JavaScript beginners who want to practice their object-oriented programming skills on a fun, visual and interactive project. Let's go! If you want me to make more projects like this one, you can let me know by clicking the like button. It helps a lot, thank you. As usual, we start with a normal, generic blank web page where we link CSS style sheet, create a HTML5 canvas element with an ID of canvas1, and we link script.js file. In style CSS, I give canvas a border. I put background PNG image into my project folder and I use it as a background for my canvas. You can download all project art assets in the resources section below. I want the canvas in the middle of the page, both vertically and horizontally, so I use the absolute positioning technique, for example. Everything else will be done with JavaScript in script.js file. We will use images and other resources in this project, so we need to wait for all of the assets to be fully loaded and available before we run any JavaScript code that depends on them. For that reason, I will put my code inside a callback function on a load event listener. When a load event fires and all resources are ready, we will run a JavaScript code. First, I point JavaScript towards my canvas element using its ID. I set context to 2D, as usual. We always have to do this line when we're setting canvas up. We are making a 2D game today. I set canvas to 800 × 800 pixels here, which will reveal the full background artwork. I can define my planet class up here outside the event listener, as long as I make sure I only instantiate that class from inside the load event listener later. Let me show you. All objects in this project will need x and y coordinates and radius, because everything will be a circle and we will be detecting collisions between them. Draw method will take context as an argument to specify which canvas we want to draw on and also to keep our classes as self-contained as possible. And inside we will draw a circle representing the planet. We pass arc method x and y coordinates of the center point, radius of the circle, start angle of the circular shape path, and end angle, which will be math.pi times 2, a full circle in radians. We call fill method to fill the path with the default black color. Inside the load event listener, I instantiate the class using the new keyword. Now I can use this planet variable, which holds an instance of planet class, and I can call draw method we defined on line 7. It expects context, so I pass it ctx from line 15. We have our planet here, drawn at coordinates 200, 200. I can change its radius. I can stroke it instead. Let's set stroke style to white and maybe line width to 2 pixels. We can move it around and resize it by adjusting these values. So this is our planet class. I actually want to have a main game class, the brain of the codebase. We will draw, update, and control everything from here. Constructor will expect canvas as an argument. Inside, we convert it to a class property, and from that property, we will extract width and height, because I want width and height properties of our main game object to be the same as the width and height of the actual canvas element that we will be drawing and animating the game on. Instead of creating a variable called planet and instantiating planet class that way, I will create a property here called this.planet. Game class will also have a render method. This method will be called over and over for each animation frame, updating and redrawing our shapes and objects. We will need context as an argument. Inside, I will take this.planet property from line 19, which now holds an instance of planet class, and I call its associated draw method from line 7, passing the context argument along like this. So now we are taking this planet class and we are instantiating it inside the game class constructor. I can delete these lines and instead I will create an instance of game class. It expects canvas as an argument, so I pass it canvas from line 27. Through that, game will now have access to width and height properties of canvas, and width and height of game is automatically set to 800 times 800 pixels. I can take that game variable from line 34 and I can call render method from it. We defined it on line 21 and we can see it expects context as an argument, so I pass it ctx from line 28. Important thing to understand here is that the code inside a class constructor is executed once, at the point when we create an instance of that class using the new keyword. So when I create an instance of game class here on line 34, it also automatically runs all the code line by line, and an instance of planet class is created and saved as this.planet property here on line 19. I like to do it this way. I think it's cleaner and easy to navigate in. Structuring our code like this in classes and objects is called object-oriented programming. This entire project will be a simple object-oriented code base. Now, planet class is connected to game class, and I can still change properties of the planet by adjusting any of these values. These same properties can now also be accessed from inside game object through this.planet property, which will become important later. What if I want this connection to be two-way? I also want the properties that sit inside the game class to be accessible from inside the planet class. I do it by passing a reference that points towards the main game object to the planet class constructor, like this. Keep in mind that objects in JavaScript are so-called reference data types, so by doing this, I'm not creating a copy of the game class here. I'm just creating a reference that points to a space in memory where the main game object sits. So when any properties that sit on the main game object update their values, those changes will be immediately visible from inside the planet class. Planet class constructor expects a reference to game as an argument, so here, where I call the planet constructor, I need to pass it that game reference. Since we are inside that game class, I pass it this keyword, which, when used here, represents the entire game object. Now we have a nice and simple two-way connection between planet and game classes. We can test it by accessing width property from line 18 from inside planet, because I want the planet to be exactly in the middle of the game area. Game.width times 0.5. If what we are covering here is too fast or too complicated for you, check out the previous class where I go much slower in a beginner-friendly pace. For the rest of this project, I assume you already know the basics of JavaScript and object-oriented programming. You can download the planet image in the resources section below. I bring it into the project as an IMG element here in index.html. I give it an ID of planet. We can see the image here. I want to hide it. We will draw it, but with JavaScript on canvas, not like this. There will be more images in the project, so I will put all of them inside a div with a class of hidden. In CSS, I set this hidden div to display none. Great. We will bring it into the project here as this.image property on planet class. Now I can call built-in drawImage method and I pass it the image we want to draw and x and y coordinates where to draw it. On canvas, x and y of a circle represents the center point around which the circle is drawn, but with rectangles and images, on canvas, x and y coordinates define its top left corner. If I want to align the rectangular image over the circular hitbox, normally I would offset it by radius, which for all other objects in this game will be exactly half of its width. But for the planet image, I made it a bit larger because we have these clouds around it and I don't really want those clouds to be active in collisions. Enemies and asteroids will only collide with the planet when they hit the actual body of the planet, not the clouds. For that reason, I have to offset it by a bit more, let's say by 100 pixels. Now we aligned the circular planet hitbox over the rectangular image. We will keep the white circle for now, it will represent the collision area of the planet. As we said before, any code inside a class constructor is automatically executed at the point when we create an instance of that class using the new keyword. I'm already taking advantage of that and I'm automatically creating an instance of planet class at the point when I create an instance of game class. At that same point, when we create game using the new keyword, I also want some event listeners to be applied. We will listen for mouse move event. Normally with event listeners, we would create a standard callback function and some code to be executed inside every time a mouse move event fires. The challenge here is that I'm putting the event listener inside a constructor on an object. We are inside game class and we are calling the event listener from window object. With a regular callback function, we would lose access to this dot properties that sit on the game class. To keep that access, to make sure that this event listener remembers that it was lexically defined inside the game class, and to allow us to manipulate this dot properties on game class from a callback function on this mouse move event listener, we have to either bind the function or, much simpler, we can use ES6 arrow function syntax here, because one of the special features of arrow functions in JavaScript is that they automatically inherit this keyword from the parent scope. It will have the auto-generated event object as an argument. I give it a variable name, for example, E. And since this function has only one argument, the brackets are not mandatory. I can delete them like this. Now, whenever mouse move event fires, auto-generated event object will be created. Let's console log that object so we can inspect it. Because we put the event listener inside the game class constructor, the event listener will be automatically applied when this line of code runs, when an instance of game class is created using the new keyword. Now I move mouse over canvas and I see those objects every time a mouse move event ticks. If I open the mouse event object, I see it contains all kind of information about the mouse event that just happened. What I need is the x and y coordinates of the mouse. We can see those properties here. I want those mouse coordinates to be available all over my code base, not only from inside the mouse move event listener. So I will create this.mouse object on the main game class, and I give it x and y properties. We used ES6 arrow function here, so we can use this dot from inside the callback function, and I can actually take this.mouse.x from line 25 and I can set it equal to e.x, to the current horizontal x position of the mouse. I also do the same for the vertical y coordinate. Okay, so as we move mouse over canvas, we are taking x and y coordinates from the event and assigning them to our custom this.mouse property to make them available all over the project. We can test how accurate these coordinates are by drawing a line from the middle of the planet to the mouse. We want to draw a simple line, so we start by begin path. Move to method will define the starting x and y coordinates of the line. It will be the middle of the planet. Line to method will define the ending coordinates. It will be the current mouse position. Now we stroke that line to actually draw it on canvas. The line doesn't react because we are calling render method only once on the first page load. We want to call it over and over for every animation frame to see some movement. Let's create a simple animation loop. Custom function I call animate. We put this render call inside. Then we call built-in request animation frame method, which sits on the window object, but that part is optional. I can delete it. JavaScript knows where to find that method without us having to tell it that it's on the window object. I pass it animate to create the loop, and I call it once on the first page load like this to actually kick off the first loop. Now, as I move mouse around, render method runs and draws line from the planet to the mouse, as we defined on lines 38 and 39. It looks like this because we see old paint. We see all the previous animation frames. We actually only want to see the current animation frame, so I delete the entire content of canvas between every frame by using the built-in clear rectangle method. We clear the entire canvas from coordinates 0, 0 to width and height of the canvas area. Now we are animating the line and we can check if the coordinates we are capturing from mouse event line up with our game objects. It's all good now, but look what happens when I make the window larger. Because canvas is not full screen, those x and y coordinates don't account for the white space between the web page and canvas element, and suddenly the coordinates are completely wrong. The line no longer goes from planet to the mouse. We can offset those mouse coordinates by accounting for the white space around canvas manually, or even easier, mouse event object already does that for us automatically, and it gives us those adjusted coordinates. Instead of using these x and y properties, we will use offset x and offset y from here. I replace them here. Now the line will go exactly from the mouse to the middle of the planet. We know we are capturing the correct mouse coordinates. Perfect. Offset x and offset y properties are useful for projects where your canvas is not full screen. I delete the console log. Time to create the player class. Its job will be to manage visuals, behavior, and controls of the player. I'm not sure if I made it clear, but we already have a fully animated code base. I'm not animating and moving the planet around, but I can already do that if I want to. Look at this. We know that render method runs over and over for every animation frame, so I can increase the horizontal position of the planet by 1 pixel per frame, and we get movement. This codebase is already fully ready for all sorts of animations. I'm just not moving things around yet. I can move the planet horizontally, I can move it vertically, down and up. It just looks static now because I'm not moving things around yet. We will get there soon. Same as we did with the planet class, I need access to properties and methods that sit on the game class from inside the player class. So I will create a property, a reference, pointing towards the main game object. As we said before, all active objects in our game need to have x and y coordinates and radius, so that we can use these values for collision detection between circles later. Also, all objects in this codebase from now on will have radius of 40 pixels. Radius is half circle, so the rectangular sprite frames will be 80 times 80 pixels. Art assets from this project are fully compatible with the main Space Invaders game we built before, so feel free to take them and use them in that project as well if you want. I will show you a fun way how to do that in a bonus lesson on that project, but I'm sure some of you can figure it out even without my help. It might be fun to add the unique enemy type we will be implementing in this project to that previous project as well, just as an exercise. I made sure it's all compatible. As usual, player will have a draw method, and we will draw a circle representing the player. Whenever we draw a circle, we have to start with the begin path. We use arc method to map the path, and we actually draw it on canvas using built-in stroke or fill method. So this is the player class. We will just repeat the pattern we did with the planet. I instantiate it as this.player property here. We will call player draw method we defined on line 24 inside render, like this. Player will move around, so I will need an update method. If I want the planet to move around in some way, for example rotate, I would have to give it update method like this as well. For now, let's just increase the horizontal X position of the player by 1 pixel per animation frame, just to test it. I call the update method we just defined from here. Player is moving because render is called over and over from inside animation loop here on line 75. We could also attach player's horizontal position to the mouse like this. I want the player to rotate around the planet and always face the direction towards the mouse. This part will be a bit more challenging to implement for beginners, but once we get that to work, the rest of the game will be easy. First, I will bring the player image into the project. You can download it in the resources section below. I give player class this.image property and I point it towards that new image we just included. I call built-in draw image method and I pass it the image and x and y coordinates. Now, if we move the player, both circle and image move together like this. I want to offset the rectangular image so that it sits directly on top of the circular hitbox. So I offset x and y by the half of the player width and height by the radius value. I prepared all art assets for this project at specific sizes that we will need in the game. Doing this saves me a lot of work now while I'm coding because the images are ready to go and I don't need to scale or resize anything with code, which would be wasteful anyway in terms of performance. So I want to move the player around the planet depending on where the mouse currently is in relation to the planet. We will write all that logic in a reusable method I call, for example, calculateAim, calcAim. Doing it this way, we will be able to reuse this method later to make enemies face towards the planet as they attack us. CalcAim method will take object A and object B as arguments, and it will calculate a vector, a direction between these two objects. So let's say we have two objects that have x and y position, for example the center point of the planet and a mouse cursor. These two objects sit somewhere in the game area. We want to calculate the distance between these two objects on the horizontal x-axis first. It will be the horizontal position of object A minus the horizontal position of object B. We do the same for the vertical axis. Now we have two sides of an imaginary right triangle and we want to calculate the distance between these 2 points, in this case between planet and the mouse, for example. We are calculating a distance between 2 points in a 2D space, so we need to calculate a hypotenuse of this imaginary right triangle. Right angle would be here. This is the hypotenuse of the right triangle, the longest side opposite to the right angle. This is a perfect use case for Pythagoras theorem formula, which would look like this in JavaScript code. But since we are using JavaScript, it's even simpler because we have a built-in math.hypotenuse method available. We just need to pass it this side, and it will give us the length of hypotenuse, which in this case is the actual distance between object A and object B. We passed here as arguments. Now I need just two very small numbers that point in a certain direction vertically and horizontally, and combination of these two values will give us a direction vector between object A and object B. We will use that to make the player spaceship point away from the center point of the planet towards the mouse cursor. I will reduce my vectors to a value range between -1 and +1 by checking the ratio between dx and hypotenuse, the distance. That will be the horizontal direction. Because the distance, the hypotenuse, is always more than dx, and because mouse can be to the left or to the right from the planet, the resultant value here will be anything between -1 and +1, but it can never be more than 1, because dx is always less than distance, less than hypotenuse. Keep in mind that the mouse can be to the right of the planet, but also to the left, like this, for example. So that's why the resultant ratio value can be negative as well. Anyway, now we have everything we need. We know in which direction we need to push an object, if we want to push it towards another object or away from another object. Aim X and aim Y values are telling us that horizontal and vertical push. I will make this calc_aim method return an array of values, because we will need multiple values from here to position the player hitbox and then to correctly rotate the player image. We have to remember in which order we are returning these values. We know that when we call calc_aim, it will return an array where the element with an index of 0 is the horizontal direction between object A and object B. Value with an index of 1 is the vertical direction, the vertical vector. Index 2 is the distance between A and B horizontally. Index 3 is a dy, the distance between object A and object B vertically. I know this was a lot of math, sorry, we are almost done now. If this is your first time using this technique, don't worry about it too much, just follow along what I'm doing. If you need to use it more often for other projects, it will eventually make more sense to you. Repetition really helps with this. For now, just understand that we wrote a method that gives us a distance between 2 points in a 2D space, and we will now use those values to point and rotate objects towards or away from each other. I want to move the player around the planet, always facing the mouse. I can implement this in many ways. For example, I can give the player this .aim property. For every animation frame, I will set this .aim property to that custom calc_aim method we just wrote. So we will make it calculate and produce those 4 values and return them as an array. That method gives us the distance and direction between 2 points, so I want to check those values between mouse and the planet. The relative position between mouse and the planet will determine where the player is facing. I will console log this.aim and we will get that array with 4 values that calc_aim method returns. For performance reasons, it would actually make sense to only update this.aim only when mouse move event fires, because if the mouse doesn't move, we are recalculating the same value over and over for each animation frame, which is not necessary. As we said before, calc_aim method returns horizontal direction, vertical direction, horizontal distance, and vertical distance, in this case between mouse and the planet, because those are the 2 values we passed to it as object A and object B. All good here, so I delete the console log. Now I can use these values to rotate the player towards the mouse. Horizontal position of the player will be always starting from the middle of the game area, which in this case is also the horizontal X position of the planet, the center point of the planet circle. We just want to add to it that small directional vector value, but because that value is very small, between -1 and +1, we would barely see the motion, so I multiply it times, let's say, 50. Perfect, that already works horizontally. I can do the same for the vertical Y position. We go from the center point of the planet towards the mouse, and we enhance that vector again by multiplying it times 50. Yes, that works. The number we use here to multiply the vector by will now influence the distance between the planet and the player spaceship. Let's say I want the distance to be equal to the radius of the planet. We get some interesting motion if the vertical and horizontal values don't match like this. It would be useful if the planet was elliptical, for example. Now, the center point of the player's circle moves along the radius of the planet circle. If I want to move it out of the planet completely, we have to push it by half of the player circle further. So plus player radius, like this. We need to use brackets to make sure the addition happens first, and then the resultant value is multiplied by the vector. You can play with the values if you are coding along, and it will make it clear what's happening. We don't need this line anymore. We also want to rotate the player image to always face towards the mouse, away from the middle of the planet. I will give player a property I call, for example, this.angle. When you call canvas rotate, it will transform canvas state, so everything drawn after that rotate call would be rotated. We only want the spaceship image to rotate, so I restrict any changes to canvas state by wrapping it between built-in save and restore methods. We save the canvas state, we do any changes here, then we call restore and reset everything so other shapes drawn on canvas after remain unaffected. Canvas rotation is a bit unintuitive if you never saw it before. Basically, remember this. To rotate something on canvas, first you have to translate rotation center point, which is the same thing as coordinates 0, 0 on canvas. You have to translate that over the coordinates of the middle of the object you want to rotate. Then you call rotate, you pass it angle you want to rotate by in radians, and then you draw that object you want to be rotated. But we draw that object not at its x and y coordinates, but at coordinates 0, 0, because the actual position of the object is now expressed in the values we passed to translate. I think it's safe to say that canvas rotation is much more complicated than CSS rotation, but it's actually easy if you do it a few times. Let's actually do it in code. I want to rotate the player's spaceship, so I translate rotation center point over this.x and this.y coordinates of the player. Rotation center point is also coordinates 0, 0 on canvas, so now I'm pushing player too far because I'm expressing its position here by translate, and I'm pushing it even further from there by these this.x, this.y coordinates. This might not be the best example to teach someone rotation because we have the player spaceship image here and also the hitbox circle, so there's a lot going on here. X position of the circle is 0 and the X position of the image is minus radius because of the difference between how rectangles and circles are drawn on canvas. X and Y is the center point of a circle, but it's a top left corner of a rectangle or image when we're drawing shapes on canvas. Anyway, now we fixed it and we are successfully translating rotation center point over the player spaceship. Now, when I rotate, it will rotate from the middle of the player image, which is exactly what I want. Built-in canvas rotate method takes the rotation angle value in radians. I pass it this.angle from line 25. So this is rotation by 0 radians. Math.pi will rotate the spaceship like this by 3.14 radians, which is approximately 180 degrees, half circle. Math.pi times 2 is 6.28 radians, 360 degrees. We rotated the spaceship all the way around. Half pi is 1.57 radians, or approximately 90 degrees. So we are facing upwards now. I hope it makes sense. We need the angle to be value between 0 and 6.28 radians, between 0 and 2 pi. And we need that angle value to match the direction between mouse cursor and the planet center point so that the player is facing towards the mouse. For that, we have another useful built-in method called math.atan2, which gives us a counterclockwise angle in radians between the positive x-axis and a line projected from coordinates 0, 0 towards a specific point, towards specific x and y coordinates. The resultant value is actually a value between minus pi and plus pi. Important thing to note here is that we pass it dy first, and dx second. So we pass these arguments the other way around. This is just how the built-in method works. We are already calculating these values in calc_aim method, and they are being returned as values with index 2 and 3 in this array, because we count indexes in array from 0, 0, 1, 2, 3. I don't have to run calc_aim method again. We are already running it on line 38, so I will just take this.aim that holds that returned array, and I take element with an index of 2 and element with an index of 3, dx and dy values. Okay, so we can see that it's kind of working. This is useful for so many things in creative coding and game development, by the way. I need to fix this. Just bear with me a second until I figure this out. How about if I swap these two values? Trigonometry, huh? Can be tricky. Okay, so that did that. If I multiply these values by -1, right, give me one more second. Okay, I made a mistake here. I said that math.atan2 needs dy first and dx second, but yeah, I'm passing it dx and dy. I need to swap them around. Yes, this is exactly what we need. Perfect. This was a lot of math. If you made it this far, the rest of the project will be easy and fun. We did the most challenging part already. Now we have our reusable calc_aim method, and we can use it again whenever we need to get a distance between two objects and point them towards each other, or make them move away from each other. I will show you how to do that when we implement enemies a bit later. We define event listeners here. Let's implement another event listener, this time for a key-up event. Inside, I console log the auto-generated event object. Now, when I click on canvas and I start typing on the keyboard, we see the key that was pressed. I can say if the key that was pressed is a lowercase d, set this.debug property to true. We will create this.debug here, and when we press letter D, we will actually set this.debug to its opposite, exclamation mark like this. I console log this.debug, and when I press D on my keyboard now, I toggle debug mode on and off. If it's true, pressing letter D will set it to false. If it's false, it will set it to true. This trick is useful for many other things as well, so it's good to remember this technique. Inside the draw method on player class, we are drawing the player image, the spaceship, and we are also drawing a circle around it. This circle will represent the collision area, player's hitbox. It's a useful thing to see sometimes, but I want to have a way to show and hide it. So I will say, only draw the collision area circle around the player if debug is true. So now, when I press letter D over and over, I'm showing and hiding the hitbox. It's the same with the planet. We have the planet image and white collision circle around it. Let's only draw it when this.game.debug is true, like this. Again, I can press letter D on my keyboard repeatedly and it will show and hide these collision elements. We can show and hide all kinds of helpful information in our game like this. We are now able to enter the debug mode in our project, which will help us to develop the game. And at the same time, we can easily hide these elements to see what the final result for the user will look like when the hitboxes and maybe some other support elements are hidden. This is starting to look pretty good. We have a planet, a player that rotates around it, and we implemented a debug mode. Now I want the player to be able to shoot laser projectiles. We need to make sure those projectiles fly in the correct direction from the tip of the player spaceship towards the mouse cursor. And on top of that, we will optimize performance of this project by implementing projectiles as a reusable object pool. It means that instead of constantly creating and discarding these projectile objects as the player shoots, we will create a pool of objects and we will pull from the pool when we need them, and we will return them back to the object pool instead of destroying and deleting them. Object pool design pattern helps us to better manage automatic memory allocation and garbage collection processes. We allocate the memory just once when we create the initial object pool, which is more performance efficient. Garbage collection is an automated process where JavaScript reclaims memory by removing objects that are no longer referenced anywhere in the code. Garbage collection happens automatically, and it can sometimes happen at inconvenient times. For example, at a time when we need to animate a large enemy wave, and as a result, it can cause lower frame rate and animation stutter. We want our game to run smooth and fast and to always respond quickly to player inputs, so we will completely eliminate the garbage collection process by reusing the same, let's say 20 projectile objects over and over, rather than discarding the old ones and creating new ones. This simple performance enhancement technique can do a lot for your projects. Let's learn how to implement it on projectiles, and when we understand it, we will use it for enemies as well. Class projectile will be used as a blueprint to create that initial pool of, let's say, 20 reusable projectile objects. As usual, we need a reference to the main game class to get access to properties and methods that sit on the main game object. Projectiles will be involved in collision detection, so we need to make sure they have x and y coordinates and radius property. I will make them large at first, so we can clearly see them. The objects created by this projectile class will be so-called object pool members. We need to give them a property that indicates whether the object is available in the pool or if it's currently being used. Initially, free property will be set to true. Projectile object is sitting in the pool, inactive. It's waiting to be used. It's ready and available. It's free. Every object pool member needs two methods. Start method that will run when we pull the object from the object pool and make it active in the game. At that point, we set free property to false. This object is no longer free and available. It's being used, drawn, and animated in the game. We also need a reset method. Instead of deleting the object when we are done with it, we will call its reset method that will set its free property back to true. It means the object becomes inactive, ready to be used again when we need it. So when we shoot a projectile, we will call its start method to activate it. When the projectile collides with an enemy or when it flies off screen, we will call its reset method to deactivate it. We will give it a draw method. We will only draw the object when its free property is false, when it's active in the game. We don't want to draw it when it's just sitting in the object pool waiting to be used. Update method will move the projectile around. Again, we only want to run the update code for active projectiles, so if this.free is false. Inside the draw method, we draw a circle representing the projectile. Begin path, arc method. Don't get confused here by the line breaks, it's all on one line. It just breaks for me to another line because my code editor window is too narrow, because I want to show you the code and the project side by side. Inside update, if the projectile is active, we will update its x and y position by speed x and speed y values. I created the horizontal speed property and I set it to 1 pixel. 1 pixel per frame means it will move from left to right. Speed y will also be 1 pixel, which means movement from top to bottom. These two speeds will combine to determine the final direction, and the combination of these two particular speed values, 1, 1, will result in a motion in the bottom right direction. The projectile class is ready. It is an object pool member. It has a free property, start and reset methods, and the code inside draw and update only runs when the object is active, when its free property is set to false. We will manage the object pool from inside the game class, from the main brain of this codebase. Projectile pool will be an array that holds all active and also the inactive projectile objects. Number of projectiles will determine how many objects we want to create and have available in the pool. If we have too few of them, we can run out and don't have any available when we need them. If we create too many, we might be wasting memory if we are never using a large portion of the pool we created. We will get to the right number later when the game is playable and we can test how fast we are using and reusing them. As the game is created, we will automatically run a custom method I call createProjectilePool, which will fill projectile pool array with 5 inactive projectile objects. I will write that method down here. Inside, I create a for loop which will run 5 times. Each time it runs, we take projectile pool and we push new projectile inside. I can see it needs game as an argument, so I pass it this keyword. So the main game class will manage our projectile pool. We store 5 object pool members in projectile pool array and we create them on the first page load as soon as we create the game object, because as we said before, all the code inside the class constructor is automatically executed when we create an instance of a class using the new keyword. We need a method to create that projectile pool, and we also need one more method. I will call, for example, getProjectile. When we call this method, it will cycle over the projectile pool array we created. As we cycle through the indexes in the array we created earlier, as soon as we find the first projectile object with 3 properties set to true, we know this object is currently inactive. It's free and available, so we take it and we return it. GetProjectile method finds the first free object in the pool and it returns it. Again, please don't get confused by the line break-in here. It's all on one line. It's just that my browser window is too narrow. So if free is true, getProjectile method returns the object and it stops searching. Initially, all projectiles are free. They are inactive and free to be used. If we run start method, we activate them and they are no longer free. I add one more event listener, this time for a mouse down event. When we click the left mouse button, on mouse down, set mouse X and Y to X and Y of the event and call shoot method on the player class. This.player is accessed through this reference. Here is that class, so let's give it a custom shoot method. When we shoot, we create a temporary helper variable and we set it to that custom getProjectile method we just wrote. We access it through this.game property here, and it sits on the game object down here. This method cycles through the pool and it returns the first free projectile object. Let's say we are currently drawing all projectiles. They are all currently active and we run out of free available ones. That could break our code, so to fix that I say if we found a free projectile, if getProjectile method was actually able to find one that is free and available, and only then take that free projectile and call its start method to activate it. Here, some properties of the projectile object change values as we animate and update it. We need to reset them to default at some point. We can choose to do it when we activate it, but also when we deactivate the object. I will do everything inside the start method when we activate the object. It will be simpler to implement in combination with other choices we already made with this particular code base. So start method will expect X and Y coordinates as an argument, and we set those values as this.x and this.y. At first, let's start all projectiles from coordinates, let's say 100, 100. I should have also console logged the pool just to check if, after this method runs, it was actually filled with 5 objects. All good? I inspect one to make sure we don't have any errors here. If you see any none value, not a number, it could mean we have a problem somewhere as we calculate these values. All is good here. I delete the console log. Inside render method, I delete this begin path. I take the entire projectile pool array, and for each projectile object inside the array, I call its draw method, passing it context, and I also call update. If I click, nothing happens, so I follow the code to find my mistake. First, I check if this mouse down event is actually running. Quick console log will help me here. Yes, I know the problem is not here. The next step would be to see if the shoot method is actually running. I console log projectile from inside here. When I click, I can see that getProjectile method is correctly returning projectile objects from the pool for me. Great, that means the problem must be somewhere on the actual projectile class. I come down here and I see I forgot one line. Arc method doesn't actually render shapes on canvas. To actually draw it here, I need to call either stroke or fill. Now, when I click on canvas, we are drawing projectiles. I want to give them a different color, but I want that color to be restricted only to the projectile drawing code and don't affect any other shapes we draw on canvas later. So I wrap this code between save and restore methods. I set fill style to gold. Projectiles move towards bottom right because of the combination of these two speeds. 1 pixel to the right and 1 pixel down per animation frame will result in this direction of movement. Start method expects x and y coordinates as arguments. I actually want the projectile to start from the player who shoots them, so I pass it this.x, this.y, because here we are inside that player class. That worked. If I keep clicking the mouse, we shoot 5 projectiles, and after that, instead of returning a projectile, getProjectile method starts returning undefined. It's because we run out of objects in the pool and it can no longer find any free available objects. There is no projectile object with free properties set to true anymore because we activated all 5 of them. I will make sure that projectiles automatically reset when they move off screen. If the horizontal x position of the projectile is less than 0, or if it's more than game width, or if the vertical position is less than 0, or if it's more than game height. If any of these 4 conditions is true, we know the projectile moved all the way to the edge of the screen, so we can call its reset method, which will set its free property to true. It will deactivate it. It also means that because of these checks, that projectile will no longer be drawn and updated. Now I can shoot. If all 5 projectiles are active, we are still getting undefined if we click more, but as soon as one of them moves off screen, it gets reset and we can reuse it and we shoot it again. Great job, we have a working reusable object pool. Now I want the projectiles to fly in the correct direction. We already have a custom calc aim method that takes 2 circular objects and it gives us horizontal and vertical direction. We can use it to make them move towards or away from each other. We are already calculating that value from before and we are setting it to this.aim property on the player class. We can use the same value because we still want the direction of the movement of the projectile to be determined by the relative position between the planet and the mouse. We want the projectile to fly from the middle of the planet towards the mouse. First, I pass start method speed x of -1 and speed y of 1. We make sure that start method expects these values and it sets its speed x and speed y properties to those values. They are being added to its position coordinates here. -1 pixel per frame horizontally and +1 pixel per frame vertically will result in this direction of motion. -10 and +1 will give us this. Let's use the values we get from calc aim method. We know that vertical vector is index 0 in the array and the horizontal vector is index 1. We are using these values, which are the ratio between horizontal distance and hypotenuse distance. Now we can fire projectiles in any direction. They move quite slow. I can create a speed modifier property. And as long as I multiply both of them by the same modifier value, it will just scale the vector, keeping that correct direction. We are running out of projectiles, so let's create some buffer. Maybe I want to create 30 in the pool to make sure we don't run out. It does depend on how fast they move off screen and how fast they reset. We can test it and adjust the value later. The projectiles come from the middle of the player circle, which is not ideal. I want them to come from the tip of the spaceship. Here on the player class, inside shoot method, we extend the starting x coordinates of each projectile by that horizontal vector value scaled to the player's radius. That should sort it horizontally. I also use the vertical vector here. It's all on one line. I hope you can read my code. We are passing a lot of stuff to the start method now. I'm using radius here because I want the projectiles to come directly from the tip of the player's spaceship. If you use different values here, like this, it should make more sense what exactly is happening here. If you play with these values for a while. If I use this dot radius here, and here, the projectile will come out from exactly the point that I want. We shoot when we click. Alternatively, I can also say if the key that was released is number 1 on the keyboard, or any key that you choose, also call player shoot. Now I can shoot by clicking the mouse or by pressing a key on my keyboard. Every time we shoot, getProjectile method will reach into projectile pool array from line 107. It will give us one free projectile object. Start method will position it at the tip of the player spaceship, and calcAim method will give it horizontal and vertical speed that matches the relative distance at the point in time between planet and the mouse to send the projectile out in the correct direction. As soon as projectiles move outside the canvas area, we reset them, and they are ready to be reused whenever we need them. We implemented an object pool in our codebase. I make them move faster and I make them smaller. Yes, this is closer to what I actually want them to look like in the final game. I can delete this console log now. Now that we saw how to implement an object pool in our codebase, let's solidify that knowledge by repeating the same logic to create a reusable pool of enemy objects. Remember that each object pool member needs a property that indicates if it's active or inactive. We only draw and update if it's active. Start method will activate the object. It will set properties to some values that the object needs at the start of its life cycle. In this case, we position the projectile depending on the player position, and we give it a direction of movement depending on the mouse position. Reset method is here to deactivate the object. We have an array that holds the objects. We set the number, and we need two helper methods, one to create the pool and another one to get a free item from the pool. Let's implement something very similar for enemies to solidify this knowledge and clarify anything, in case you're still not entirely sure how some of this works. Repetition always helps. I create an enemy class. It needs a reference to the main game object. It needs x and y and radius. For example, let's set the starting x and y coordinates to 100, 100, just for now. We will be cropping rectangular frames from a sprite sheet by jumping by the width and height of the frame around the sprite sheet. I created the art assets to match what we need in-game. Collision circles have 40 pixels radius, so individual sprite frames will be 80 times 80 pixels. This frame size also matches the Space Invaders game we did before, so these enemy sprite sheets are fully compatible and can be easily used in that game as well if you want to expand it. Speed X and Speed Y will determine in which direction the enemy will be moving, and since this is an object pool member, it needs free property. Initially, we set it to true. Start method will set free to false to activate it, and reset method will set free to true to deactivate it. Draw method will expect context as usual, and the code inside will only run for active enemies. Update method will also run its code only for the active ones. At first, let's draw the enemies as simple circles, so the usual combo of begin path, arc method, and I stroke them. Update method will move its x and y coordinates around depending on speed x and speed y values. Same as we did for projectiles, we need an array that will hold all active and inactive enemy objects, enemy pool. Number of enemies will be 20, and we will automatically create and fill that pool with 20 enemy objects at the point when we create an instance of game class. Same as we did for projectiles, create enemy pool will create and push 20 enemy objects into enemy pool array. Enemy class constructor expects game as an argument, so I pass it this keyword. GetEnemy will cycle over the enemy pool array we just filled with 20 inactive objects. I will check free property for each one, and as soon as it finds the first enemy object with free property set to true, it returns that object and it stops searching. I console log enemy pool. At this point, it should be filled with 20 enemy objects here after we called the create method. Yes, I see them. I open one just to check. All seems good here. I delete the console log. Same as we draw and update projectiles for each animation frame, we take enemy pool, call for each on it. For each enemy, we call its draw and update. And we remember that these methods will only run if the object is active, if its free property is set to false. Initially, all enemy objects have a free property set to true. Calling start will activate the object. I want the first object in the enemy pool array to be automatically activated immediately as the game starts. So I take one object with an index of 0 inside enemy pool array and I call its start method. I can see it here. Let's activate the first 5 objects. To do this, we have to be careful. If we don't have enough objects in the pool, this would break the code because I'm not doing an if statement check first. Make sure the number here is high enough. I'm drawing all 5 enemies at the same coordinates. If I move them, all of them move. I could set the starting x and y coordinates to 0, 0, and when start method runs, let's set x to a random value between 0 and game width, and vertical y position to a random value between 0 and game height. Now, when I refresh the page, the 5 enemies are scattered randomly around the visible game area. As always, we are adding speed x and speed y values to their x and y coordinates for every animation frame to give them direction and speed of movement. Combination of these values will determine their movement vector. I set speeds to 0, 0. We will set their speed when start method runs. I want the enemy to move directly towards the middle of the planet. They are attacking us. We need a vector between that random enemy starting position and the planet. We already did something similar. I create a temporary helper variable called aim. It will run our utility calc aim method, but this time we want directional vectors between the enemy So this keyword, we are inside that enemy class, and as object B, we pass it the planet. If you remember, it returns an array of 4 values, where the first element, the element with index of 0, is the horizontal direction. Element with an index of 1 is the vertical direction. It doesn't work, and it's because we need to calculate the aim after we position the enemies. Enemy position is of course very important in this calculation to get the correct direction between the enemy and the planet. First, I set enemy position, then we call calc aim. Now the enemies are moving towards the planet. Perfect. I don't want the enemies to go through the planet like this. I want them to collide with it. Let's create a reusable check collision method. It will expect object A and object B as arguments. In this project, all objects will have circular hitboxes. To check collision between 2 circles, circle A and circle B, we have to check the distance between the center point of circle A and the center point of circle B on the horizontal x-axis. That gives us this side. Then we do the same on the vertical y-axis to get this side. Now, to get the actual distance between these 2 points in 2D space, we need the length of the hypotenuse, which we can get by Pythagoras theorem formula or built-in math.hypotenuse method. We have a distance between 2 points, between the center point of circle object A and circular object B. We calculate the sum of their 2 radii. If the distance between the center points is more than sum of radii, we know that the circles don't collide. If it's the same, the circles touch. If the distance is less than sum of radii, we know that the circles collide. I will just directly return the expression like this, making this method easy to use. We call it, we pass it object A and object B, and this method will directly return true or false, depending on whether or not these 2 objects collide. Let's see if it works by going up to the enemy class, and inside the update method we check collision between enemy and planet. When collision happens, we will reset the enemy, which will deactivate it and returns it back to the pool of available objects. I copy this code block. We do the same thing for the player. If enemy collides with the player spaceship, we reset the enemy. Let's see. Yes, that works. When we reset the enemies, they are gone, but now I need more enemies to keep coming. Right now, we only activate the first 5 enemies from the pool here. I want to activate new enemy periodically, let's say every 1 second. Request animation frame method automatically generates a timestamp, and it passes that timestamp value as an argument to animate method. Imagine it's passing it here like this, even though it happens invisibly behind the scenes. The timestamp value is simply the number of milliseconds that passed since the first request animation frame in this sequence was called. All we need to do to get access to that timestamp value is to give it a variable name here, and the JavaScript will automatically know that we wanted the timestamp. We also need to keep track of the timestamp from the previous animation loop. I will call it last time. I put it outside animate here, and initially I set it to 0. Then we use these values to calculate delta time. Delta time is the number of milliseconds it takes our computer to serve 1 animation frame. It's the difference between the timestamp from this animation loop and the timestamp from the previous animation loop. If you have a fast computer, your computer can serve frames faster, so your delta time will be lower, because that fast computer needs less milliseconds to generate each animation frame. Request animation frame method also automatically normalizes the animation speed, And if it can do it, it will adjust animation speed to the screen refresh rate, because there is no point to calculate and draw animation frames that your screen isn't able to display. Once we calculated delta time, we set last time to the current timestamp so that it can be used as the old timestamp from the previous animation loop in the next animation loop. Most of us have screens that serve 60 frames per second. 1000 milliseconds divided by 60 is around 16.6, so my delta time is 16.6. My animation is running at 60 frames per second. If you have a high refresh rate screen, or if you have a very old, weak computer, your delta time might be different than mine. Using delta time like this will make sure we account for that, and we count the actual time, the actual milliseconds. This allows us to make sure the timing in our game is the same on fast and slow machines. I delete the console log and I pass delta time to render method. I will make sure render method expects that value as an argument, and I console log delta time from here. Yes, it still works. Always make sure you delete your console logs. Leaving a console log like this can slow your application down. These variables relate to enemies. I will only add one enemy at the start of the game. I will need two helper variables, enemy timer and enemy interval. Enemy timer will count delta time from 0 until 1000. Then we add a new enemy and we count again. We want to periodically activate an enemy object from the object pool every 1 second, every 1000 milliseconds. If enemy timer is less than enemy interval, we keep adding delta time value to the timer for every animation frame over and over until we get more than 1000, and then this else statement will run. When timer accumulated enough delta time, we reset timer back to 0 so that it can count again, and we activate one new enemy. Helper temporary variable called enemy will be equal to our custom getEnemy method. If getEnemy was able to return a free and available enemy object from the pool, we call its start method to activate it. Nice, we are pulling a new enemy from the object pool every 1 second. I don't really want the enemies to appear somewhere in the middle of canvas randomly. Let's try something. If I call math.random on its own like this, it will return a value between 0 and 1. So if that value is less than 0.5, roughly in 50% of the cases, we set horizontal position of the enemy between 0 and game width, and vertical position will be 0. Enemy will appear somewhere in this area. Else, in the other 50% of the cases, we set x to 0, and y will be a random value between 0 and game height, so the resulting position will be randomly somewhere in this area. Nice! Now we can do it for the other two sides as well. How to do that? For example, we can use a so-called ternary operator, the only JavaScript operator with 3 operands. We use it as a simple one-line if-else statement. It goes like this: a condition to evaluate. If true, question mark, do this, else, colon, do that. So if math.random is less than 0.5, vertical position of this enemy will be 0. Else, in other 50% of the cases, this.y will be this.height. So if this code block runs, enemies will be coming from here or from here. Yes. We do the same in this code block. If math.random is less than 0.5, this.x is 0. Else, this.x is game width. While at the same time, vertical position is random between 0 and game height. If this code block runs, enemies will be coming from here or from here. Now we have enemies randomly coming from all 4 directions. When they collide with the player or with the planet, they get reset and they disappear. I also want to be able to shoot the enemies. I want to check collision between enemy and projectiles. I take the entire projectile pool array, and for each projectile object, I check first if the projectile is active. if its free property is set to false. Keep in mind that this code block also only runs for active enemies. We only want to check collision between active enemy and active projectile. If the projectile is active, we also check collision between this enemy and the current projectile we are cycling over. If projectile and enemy collide, we reset the projectile to deactivate it and return it back to the object pool. When I test it, I can see that projectiles get destroyed when they hit enemies. Great! I will also reset enemy when the collision happens. Nice! Now we can shoot the enemies. We have a full game loop and we implemented projectiles and enemies as object pool, which involved some extra logic, but it's worth it for performance reasons. And the code is still clean and easy to read, I think. I don't like how the enemies just pop in. I want that to happen off screen and the enemy just floats into view smoothly and seamlessly. I will push the enemy starting positions outside the screen. I account for the radius here, here, here and here. Now they start off screen and they float into view. Much better. I can make the enemies come more often. How about new enemy every half second? The planet is really under attack now. White circles are attacking us. Let's use some graphics. First, we do a simple enemy type, an asteroid. We can download the enemy sprite sheet in the resources section below. I give it an ID of asteroid. So this is the parent enemy class. It contains all methods and properties shared among all enemy types. I will create a child class called Asteroid. Class Asteroid extends enemy. So now enemy is a parent class, also called a superclass. Asteroid is a child class, also called a subclass. Asteroid class constructor will expect game as an argument. Here, first I want to run all the code inside the constructor, inside the parent enemy class, inside its superclass. I want to run all the code here. I pass the game reference along. We know it's expected there on line 98. Asteroid child class will contain properties and methods that are specific only to this enemy type. Asteroid will have this.image property, which will point to that asteroid sprite sheet we imported a moment ago. Shared properties are on parent class, specific properties and methods are on the child class. Because we are using the extends keyword here, JavaScript automatically sets up a prototype chain behind the scenes. So when we call draw and update method on asteroid class and JavaScript can't find them here, it will automatically travel to the parent enemy class and it will try to find those methods there. Since all enemy types will have images, I can go up here and I can call built-in draw image method. I pass it the image I want to draw and x and y coordinates where to draw it. We get an error because we are instantiating the parent enemy class and the JavaScript can't see this.image property on it. I have to create an instance of asteroid child class instead. Now we are drawing the entire sprite sheet. I will reduce the maximum number of enemies to 2 so that it's less busy and easier for us to see what's happening. We can pass drawImage method optional width and height like this. Now the entire image will be stretched or squeezed to fill that predefined area. In this case, I'm squeezing the entire asteroid sprite sheet into an area of 1 frame. We can also pass drawImage 9 arguments to get the maximum control over the image we want to draw. We pass it the image we want to draw, source x, source y, source width, and source height of the area we want to crop out from the source image, and we pass it destination x, destination y, destination width, and destination height to define where on destination canvas we want to place that cropped out piece of image onto. First, I crop out this frame from coordinates 0, 0 to width and height of 1 frame. Nice. Again, as we know, circles and rectangles are drawn differently on canvas, so to align the rectangular asteroid image over its circular hitbox, I need to offset the horizontal position destination x argument by the radius, like this. And I also offset the vertical y coordinate by the radius, like this. Planet is being attacked by asteroids now. I increase the size of enemy object pool back to 20. I want a new enemy asteroid every, let's say, 1700 milliseconds. I only want to draw the collision circles on enemies if debug mode is active. I want to be able to show and hide them by pressing D on the keyboard, by toggling debug mode on and off. We can navigate around the sprite sheet and decide which frame we are currently cropping out by adjusting the value we pass to drawImage method here. Source x argument can be like this. 0 times width of a single frame will give us this. 1 times width we get this frame. 5 times width is this frame. The way I structured this sprite sheet, horizontal navigation around the sprite sheet will play explosion animation frames. Source y argument will go up and down around the sprite sheet. 0 times height is this frame. This is 1 times height, 2 times height, 3 times height. Source y argument passed to drawImage method will determine which one of these 4 available asteroids we are drawing. I will put this multiplier into a variable I call frame y. I can put it here, but maybe each enemy type will have different sprite sheet with different number of animation rows, so I put frame y here on the asteroid subclass. I want to randomize it. Each asteroid object will be randomly assigned one of the 4 variations of the asteroid I created for you. I need to wrap it in math.floor to round it down to integers, because there is no row 1.5 for example. Frame y will be randomly 0 or 1 or 2 or 3. Since enemies are an object pool, if I play like this, I'm constantly just reusing the first 1 or 2 objects over and over, returning them to the pool and taking them again. That's why the images don't change. I can, for example, randomize the row every time enemy object is activated here, inside the start method. For now this is fine, although it can give us issues if other enemy types don't have 4 sprite rows. I can also make the enemies more challenging by giving them multiple lives. I give enemy object a custom hit method. This method will take damage value as an argument. When hit method runs, we reduce lives of enemy by damage. Here we check collision between enemy and projectiles. Instead of resetting the enemy immediately, I will call that hit method and I pass it 1 as damage. Doing this means that when we hit an enemy with a projectile, we reduce its lives by 1. If lives of the enemy are less than 1, I want to keep increasing frame x to play the explosion animation. We need to use that frame x value here. As it increases from 0, 1, 2, 3, 4, we are cropping out different horizontal sprite frames and we are playing the animation. I could put frame x on the parent class, but let's keep it on here on the child class, next to frame y. Now, when I hit asteroid 5 times and deplete its lives, the rest of the sprite sheet will play the explosion frames. Now we need to also reset that asteroid when all its horizontal animation frames are played. I will give it a max frame property and I will set it to 7. We know that once all 7 frames were displayed, we are safe to reset it and return it back to the pool. If frame x is more than max frame, we call reset. Since enemies are object pool members, we also need to reset these values as we reuse these objects. I will give it max lives property, and it will remember what was the original amount of lives of that enemy before we started damaging it. Now, when I shoot the asteroids, they don't come back because their frame x is stuck at a high value and they keep resetting. When we start an asteroid, we need to make sure its frame X is set back to 0, and its lives need to be set back to max lives. Nice, now it all works. When the debug mode is active, I want to display the number of lives as a big number drawn over each asteroid. We will do it here inside this conditional code block that runs only when debug is active. I call built-in fill text method that takes at least 3 arguments: the text to draw and x and y coordinates of anchor point in relation to which the text will be drawn. The text I want to draw is this.lives property of the enemy, and we want that number to travel around as the enemy moves, so I give it x and y coordinates of the enemy. Down here, where we set our canvas up, I will define canvas font property. Let's set it to 30 pixels Helvetica. Fill style will be white. I increase the font size. As you can see, when we position the text anchor point exactly in the middle of our circular asteroid, the text is drawn towards right top from there. The anchor point sits on the left bottom edge. Text align property defines where the text we draw on canvas sits in relation to its anchor point on the horizontal x-axis, so I set it to center. Text baseline property defines the relationship between text and its anchor point vertically. I set it to middle. Now the text is centered over the asteroid. Nice. When we destroy the asteroid, the explosion animation frames play too fast. We are using sprite sheets with limited number of frames to help us with performance. Now we need a way to slow down the speed at which the sprite sheets swap frames so that users can actually appreciate the details of the animations. We will use the same technique we used here with timer and interval helper variables. Sprite update will be false. It will switch to true periodically just for that one animation frame to allow all the sprite sheets in our game to jump to the next frame. Sprite timer will count delta time from 0 to sprite interval value over and over. Every time it reaches the interval, it triggers sprite update and resets back to 0 so that it can count again. Let's say I want to trigger sprite update every 150 milliseconds. We will write the logic to periodically update sprites here. We are repeating the same logic we used to activate enemies. If sprite timer is less than sprite interval, keep increasing sprite timer by delta time, which we are already calculating from before. It's the time in milliseconds it takes our computer to serve one animation frame. Else, meaning that sprite timer is higher than interval, it accumulated enough milliseconds through delta time, we can reset sprite timer back to 0 so that it can count again, and we set sprite update to true. I want sprite update to be true just for that one animation frame, so here I will set it back to false. Now, this code block means that sprite update is set to true for one frame every time sprite interval value that we set to 150 milliseconds is reached. When I console log sprite update, we see it is false and it is periodically set to true. Great. Every time it is true, I want to animate sprite sheets. I want to jump to a new frame in the sprite sheet. Let's not forget to delete the console log. We will handle sprite animation logic here. If the lives of the asteroid are less than 1, and only if sprite update is true, only then we increase frame X by 1. Now the explosion animation plays slower, and we can set that speed to anything we want using sprite interval property. The problem is that now when the explosion plays slower, I notice that the projectiles still collide with asteroid that is already exploding. I want the projectiles to ignore explosions. We only check collision between enemy asteroid and projectiles if the lives of the enemy are more or equal to 1. If the lives are less than 1 and explosion animation is playing, projectiles will fly through it. Yes, this is much better. I can show and hide hitboxes by pressing letter D. by enabling and disabling the debug mode. I want the asteroids to have only one life. It will be a simple basic enemy type. Our lasers are calibrated for asteroid defense and we can easily destroy each one by a single hit. Let's add a more challenging enemy type. You can download Lobstermorph sprite sheet in the resources section below as usual. I put it into my project folder and I include it here, giving it an ID of Lobstermorph. At this point it's easy to implement more enemy types because we already have most of the logic in place. I copy this entire code block for Asteroid and I rename it. I point this.image property to the Lobstermorph sprite sheet. I can set max frame to 14. We know that when we reach that point, it's safe to reset the enemy. I created these sprite sheets with a specific plan in mind. Asteroid will have one life. When we hit it, the rest of the sprite sheet will play the explosion animation. Lobstermorph will have 8 lives. Each time we hit it, we jump by 1 frame until we deplete all 8 lives. Then the rest of the frames will play in one animation sequence. Down here I comment out Asteroid class and instead I will push Lobstermorph enemy type into enemy pool array. Okay, we have some aliens incoming. I play to see what we have so far. I can press D to disable debug mode. I can see that when I hit them 8 times and deplete the lives, the entire sprite sheet plays. I can go here inside hit method and when we hit the enemy and we decrease its lives by the damage value, I can set frame X to be max lives minus the current lives. This will work already. Enemy goes to a new stage every time it loses a life and then the explosion plays. I can do it differently here. I can say if enemy lives are more or equal to 1, every time we hit it, increase frame X by 1. We get the same behavior. Enemies get instantly reset when they collide with the player or with the planet. When enemy collides with the planet, I instantly set its lives to 0, which will play the sprite sheet, and I also want the enemies to stop moving at the edges of the planet, so I set speed X to 0 and speed Y to 0 when collision with the planet happens. When enemy hits the planet now, they stop and they play their animation sequence. I think this looks more interesting. They play the sequence and when the current frame is more than max frame, they reset and return back to the object pool. When enemy collides with the player, I will just set lives to 0 to make it animate. I'm not going to stop its movement. You can make your own choices here. Design the game how you want it. I'm just showing you how the codebase works. We have a bug. If you console log enemy each time we activate one, you will notice some of them are stuck off screen. They're not coming from one side of the screen at all, because their horizontal position is none, not a number. It's because I set this.game.radius here. I need to use the radius of the enemy instead. You probably noticed that before. Anyway, now it's fixed. I want to rotate the enemies to make sure they face towards the planet in the direction of their movement. Every time we rotate canvas, it adds up and it affects everything drawn on canvas. So I want each enemy to be rotated by its individual angle value, so I will restrict any changes I make to each enemy drawing code by wrapping this code block between save and restore methods. We save canvas state, we make any changes here we want to be applied to these drawing calls, and then we reset back to what it was before to make sure the shapes drawn after this remain unaffected. On canvas, I can't just simply rotate. If I rotate by 0.1 radians here, you will notice that everything is a bit off. To rotate anything on canvas, first, we have to translate rotation center point, which is the same as coordinate 0, 0 on canvas, over the center of the object we want to rotate. So I translate to this.x, this.y of the enemy we are about to draw. Now that we translate it, we have to keep in mind that we are translating rotation center point as well as the point that is considered coordinates 0, 0 on canvas. We are translating it over the enemy position, and then we are going further from there to actually draw the enemy. We effectively doubled the enemy position, pushing it further to the right and to the bottom. So off screen. Enemy position is now defined by the translate, so we have to actually draw everything at coordinates 0, 0. If I draw enemy collision circles at coordinates 0, 0, we get this. I also have to do that for the text coordinates that display enemy lives, and for the actual image, which is centered over the circle by offsetting it by radius. We do minus radius here and here. So to rotate something on canvas, we translate over the object we want to rotate. Then we draw that object at coordinates 0, 0, because the object's position is now defined by translate, and now I am free to rotate it and it will work. If I rotate by 0.1 radians, 0.5 radians, instead I will use this .angle property, and I define it here. 1 radian means all enemies are rotated like this. 2 radians. I want the rotation angle to depend on the relative position between the enemy and the planet. We already wrote helper calc aim method and we are using it to set enemy speed. Calc aim method gives us directional vectors as well as dx and dy, vertical and horizontal distance between the two objects we pass to it as arguments. I will need these. I can see these are elements with indexes of 2 and 3 returned in this array. Initially I set angle to 0. It doesn't really matter because when start method runs, we set this .angle based on the relative position between this enemy and the planet. We already did that when rotating player spaceship away from the planet center point. It's the same thing here. We use built-in math.atan2 method that will give us an angle between positive x-axis and a line projected towards a specific point. We know it expects dy first and dx as the second argument, so I have to pass these arguments in this order. Enemies are not pointing where I want them to, but it doesn't matter because we know that the angle we are getting is relative to the starting position of the enemy and the planet. Start method runs just once to set the enemy up, and I can adjust that resulting value in many ways. I could rotate the entire Lobstermorph sprite sheet in my graphics editor, and then I could use that, but I could also easily do that with code. I can see I simply need to rotate the enemy by 90 degrees, by a quarter of a circle, to make sure they face the planet, so I add math.pi value here. If I add math.pi, I'm rotating it by 3.14 radians, by 180 degrees, half circle. I only want to rotate by half pi, by 90 degrees, by a quarter of a circle. Even if you don't fully understand math.atan2 yet, just remember how to use it. Pass it the points that are relevant in the rotation you want and see what result you get. Then you can easily adjust that angle further like we just did. There might be even a simpler way to do this that I'm not thinking of right now. I know some of you will give me your tricks and improvements in the comments, and I appreciate that. Anyway, enemy aliens are now facing towards the planet. Every time we hit them, we push the sprite sheet to the next frame. When lives are depleted, animation plays. Animating sprite sheets like this is very cheap performance-wise. Your game will run smooth if you are happy with a low frame rate sprite animation like this. I think the game looks alive even with this performance-friendly sprite animation techniques. I like how it reacts to player actions. It makes the game feel very interactive and responsive. DrawStatusText method will display score, player lives, and game over messages. It will expect context as an argument. Font will be 30 pixels impact, for example. You can easily use any custom Google fonts here if you want. Just import them in index.html, give Canvas that font family property in style CSS, and use the name of that font family here instead of impact. It will work. I used custom font in other games many times before, so this time let's just go with default impact font and focus on other things. I call built-in fill text method. Text will be score, coordinates will be 20, 30. I want the text to be drawn over the planet but under the player and projectiles and enemies. It will create a nice layer effect when the text is kinda in the middle of game objects. When I call draw status text and I pass it context, I can see that score text is center aligned and enemy lives are now drawn in different font. This declaration changed the entire canvas state. So again, I wrap it in save and restore so that I can give status text specific settings without affecting other text and shapes drawn on canvas. I set text align to left. I create this.score property. I go to the main enemy class. When enemy finished playing explosion animation and is reset back to the object pool, I increase the score by enemy max lives, which means easy asteroid enemy will give 1 score point, Lobstermorph enemy will give 8 score points. It has 8 lives. Here I add this.score to actually draw the value. I play. Every time I destroy an enemy and the explosion animation finishes playing, I get rewarded 8 score points. You can see that every time enemy explodes, we get 8 score points. I only want to award the player score points if we destroy the enemy by shooting it. If the enemy gets destroyed because it collided with the player or the planet, we don't want to give score points for that. I will give each enemy a property called collided. Initially, I set it to false. When we start the enemy, we always have to reset it back to false. If enemy collides with the planet, we set collided to true. Also, if the enemy collides with the player. If enemy collides with a projectile, we do nothing, which means collided will stay false. Here, we only add score if collided is false. If I shoot the alien, I get 8 score points. If the enemy collides with the player or the planet, we get no score points for that. Great. I create a property called winning score. Initially, for the testing purposes, I set it to 10. We will handle win or lose condition here inside the render method. If score is more or equal to winning score, game over is true. Down here inside the draw status text method, we will handle game over messages. If game over is true, I want 2 big messages in the middle of the screen, so we set text align to center. I can, for example, create 2 let variables called message1 and message2. They will be assigned a different text when we win and when we lose. So if we win, if score is more than winning score, message1 will say you win. Message2 will say your score is, and we display the score value plus an exclamation mark like this. Now we will draw them. Message 1 will be large, 100 pixels impact. Again, you can use your own custom font here instead of impact. Fill text method will draw message 1 in the middle horizontally and 200 pixels from the top vertically. Another fill text for message 2. Again in the middle horizontally, and let's say 550 pixels from the top vertically. Let's try to win the game. I need 10 or more score points. Nice! I want the second message to be smaller. How about 50 pixels impact? Again, I shoot enemy 1, enemy 2, and here we go. Yes, that looks better. I want the enemies to stop coming when game over happens. Only pull a new enemy object from the pool if game over is false. Now, how can we lose this game? We can, for example, give the player a limited number of lives. I put those lives here on the main game object. I go down here. Oh, this restore needs to be down here. Otherwise, the numbers we use to display enemy lives will change to 50 pixels impact when game over message appears. Now it's fixed. I want to draw player lives under the score. I create a for loop. It will run once for each life, and it will draw a rectangle for each one. Left margin will be 20 pixels. Horizontal X position will determine the spacing between rectangles, so it will be 15 pixels. And we space them out by multiplying that spacing times index in the for loop. Vertical position will be maybe 60 pixels from the top. The width of each rectangle should be less than spacing, so for example 10, and height will be 30 pixels. You can change these values to see what they do. This is the left margin. This is horizontal spacing. If the width of each individual rectangle is the same or more than the spacing, they will turn into a single bar. You can build loading bars like this if you want. I want them to be separate here, so I go for 10, I guess. If enemy collides with the planet, I take this.game.lives and I reduce it by 1. Also when collision with the player spaceship happens. I test it. When we collide, it immediately takes all 5 lives because it's taking 1 life per animation frame. We only want this code block to run for enemies that have lives more or equal to 1. We enter this code block and we set lives to 0, which will prevent the same code block from running again. This should fix it. I do the same for player collisions. Yes, now 1 collision takes away only 1 life. Perfect. Here inside win and lose condition code block, I say if score is more or equal to winning score, or if this.lives is less than 1. In both cases, set game over to true, which will stop enemies from coming, and it will display big message 1 and message 2. If we win, we set messages to these, else meaning we lost all lives, message 1 will say you lose. Message 2 will say try again. I test it. I shoot enemies. I win. Enemies collide with the planet. We are losing lives. We lose all lives and losing message appears. Great, we have a complete game loop. Initially, I will set debug to false. We can still toggle it on and off by pressing letter D on the keyboard. I want to bring all enemy types into the game at the same time. Here, where we create enemy pool, I create a random number variable. I set it to a random value between 0 and 1. If random number is more than 0.25, in 25% of cases, we create an asteroid. Else, in the other 75% of cases, we create Lobstermorph. Asteroid is the easy enemy type with 1 life. Lobstermorphs are tough enemies that morph and split, so they take longer to defeat. I want to add a new enemy more often, let's say every 1 second. I want to be able to make enemies move faster or slower. We did the same thing with player projectiles. I create a speed modifier property. I want to slow them down in this case. Speed modifier will be a random number between 0.1 and 0.6. Then I include speed modifier here, where we calculate horizontal and vertical speed. I am scaling the vector here. I prefer the game like this. We have many more enemies on the screen, but they all move slower, giving us more time to strategize. It's up to you to choose if you want the game to be more about fast reactions or positioning and strategy. You can tweak enemy frequency and movement speed based on what kind of gameplay you prefer. How about enemy interval 800 milliseconds and 30 lives? 50 winning score? I will adjust these values later. I built another space game recently, inspired by the classic Space Invaders. I made sure that the sprite sheets from that game are compatible here. Let me show you how we can take them and easily use them in this project. If you followed that class, you already have the sprite sheets. If not, you can download them in the resources section below. I import Beetlemorph sprite sheet into the project. To add more enemy types into this game is extremely easy because we already wrote all the logic. I can just copy this code block, I rename it to Beetlemorph, and I adjust this.image property. I check the sprite sheet, max frame will be 3 and lives will be 1. This enemy is easy to defeat. Down here, where I create enemy pool, I can say else if random number is more than 0.5, add Beetlemorph. I have to be careful about brackets here. I have to change the condition here. If random number is less than 0.25, we create Asteroid. Else, if the number is less than 0.5, we create Beetlemorph. In the other 50% of cases, we create a Lobstermorph. That was easy. Now the game has even more variety. Now that we understand the process, let's take one more enemy type and use it. I copy this code block and I create Rhinomorph enemy type, the armored enemy. Again, you can download the sprite sheet down below if you don't have it from the Space Invaders project. Here I add one more else if random number is less than 0.75, we push Rhinomorph into enemy pool array. My code editor colored this class name differently to remind me that I still haven't written that class. Up here, I copy this code block, I rename it Rhinomorph, I point its this.image to the new sprite sheet, max frame will be 6, it will have 4 lives. Now our game has 4 different enemy types. Simple enemies with 1 life will be Asteroid and Beetlemorph, an armored enemy, and enemy that splits into smaller clones when we hit it. I set enemy interval to 1200 milliseconds and play lives to 10. If you watched the extended Space Invaders class, over there we also have Squidmorph, an inflatable enemy that absorbs player projectiles until it pops. And we also have Eaglemorph, an enemy that sacrifices its own body segments and spits them back at us as mutated projectiles made out of slime and tentacles. All of those art assets are fully compatible with this codebase. A challenge for you is to take them, if you followed the extended class, and implement them in this game. If you want, you can also take the unique enemy from this class, the Lobstermorph, and implement it in the Space Invaders game. These two games are completely cross-compatible. I only want to increase the score if game over is false, like this. It's easy to do, and if you need my guidance, I implement Lobstermorph into Space Invaders game in the extended class. If you are watching this on my YouTube channel, the most popular and recent extended bonus classes are linked on the About page. Hope you had fun on this space adventure. This was a big project. Well done if you got this far. Let me know if you found some value and learned something new by leaving a quick comment. I wonder which part of this project was the most interesting for you. Can you just leave a quick comment and tell me which is your favorite enemy type out of all of them? It can be either what it looks like or its unique behavior and mechanics. Looking forward to see what you think and which one is your favorite. See you later.